One of the most challenging days I faced as a parent was the day my kids brought home one of these from the elementary school. The amount of inhuman sounds that this little device can make is absurd. But it does tell us a lot about standing waves and air columns, which is going to be our next physics topic for today. So if you recall, last time we looked at standing waves on a string. Today that we can also create a standing wave in a column of air. For instance, if I run air through this device, it's going to generate a sound, okay? But if I shorten up this column of air by releasing my fingers, see, even I'm not good at it. As I shorten this length up, I'm going to create higher and higher frequencies. So why is that? So when I have a column of air in a tube, let's pretend that it's open at two ends here. Here there's a little opening right here, just like there's a little opening here, just like many of your musical instruments. Okay? If that's the case, those ends are going to be where the air can vibrate freely. Those are going to represent the antinodes. I'm going to represent that with the letter A. And that means that in the middle, divided right in between those two, is going to be the node. Now, you can see that the way that this is depicted, that in order to complete this wave, I'll continue with this red color here, this would need to come back here, and this would need to come back here. And so these would be vibrating like so. So that would be a complete wave, which means that this distance L here represents only half of the entire wavelength. So if that's the case, my first fundamental wavelength is actually 2 times this length right here. I'd add half an L on here, half an L on here. The entire fundamental wavelength would be 2L. That would represent the first harmonic in this situation, which means that the frequency that would be represented here would be my velocity of that of the speed of sound in air divided by my lambda, or in this case, velocity divided by 2 times the length of this tube. Okay? Now I can go to higher and higher harmonics here by creating a higher moving speed of air here. My second harmonic, this right here, you'll notice that the way that this would be represented is actually just kind of offset a little bit. Here, my wavelength of the second harmonic is just going to be L, because this actually ends up being one complete wavelength. So this is actually going to be double the frequency that I initially had. As I go up to higher and higher harmonics, the same rules that we applied with the waves on a string are going to apply. The only difference is with an air column is that the antinodes are at the end, unlike the string where the nodes were at the end. The air is vibrating freely on the ends here, and that's why we have kind of this offset situation. So I can actually create higher and higher harmonics here by just creating a little bit more energy through there. Now, let's twist it over here a little bit. I have here, these right here, they're open at both ends. And I can keep going to higher and higher frequencies if I go with a shorter and with a shorter and shorter pipe. Now these are open at both ends. What happens if I go to a pipe that is closed at one end? Okay, so if I close this at one end, now when I look at it, watch as I compare these two. Whoops. I'll go like this. You can see that this frequency is lower, which might seem kind of odd. Let's try it with these two. Same length, but one's closed at one end. And you'll notice that it actually has half of the frequency. It's a lower pitch tube as we do that. So let's go back and see why that might be. So if I've got a pipe that's open at one end, it means it's closed at the other end. So here, the closed end is going to represent a node, okay? But the other end has to be open. That has to be where we are vibrating freely. The other end has to be an antinode. If that's the case, what this means is that my wave inside this tube is actually only 1/4 of this entire lambda. So my lambda of my fundamental first harmonic is going to be 4 times that length, okay? When I get to my next possible harmonic here, something odd happens, and I mean that quite literally. I can only create odd harmonics because now my next wave right here, this would be completed like so. And if that's the case, now this length of this tube is 3/4 L, okay? This is actually going to go from my first to my third harmonic. I completely skip my second harmonic. My next harmonic is going to be my fifth harmonic. So I go from a wavelength here of 4L to a wavelength of 4/3 L to a wavelength of 4/5 L. Notice that my wavelength in each case is just going to be an increasing denominator, but I'm going up by consecutive odd integers, 4 divided by that number, to figure out what that what that wavelength is going to be. Okay, so let's try a problem related to this. So let's assume that 343 meters per second is the speed of sound in air. What length of pipe open at both ends has a fundamental frequency of 370 hertz? Now I close one end, what's the new fundamental frequency, and what would be the first overtone of that, which for one that's closed at one end would be the third harmonic. So let's take what they've given us. The velocity of air, in this case, is 343 meters per second. The fundamental frequency is 370 hertz. My unknown is what is that length if it's open at both ends? Well, I know that for if it's open at both ends, my fundamental wavelength is going to be 1/2 of my lambda. So that means 2 times my length is going to be my lambda. Remember, our velocity equation for a wave is frequency times lambda. So if I take my velocity divided by my fundamental frequency, that's going to give me my wavelength. So I keep crunching these numbers here, and I'm going to see that if that's the case, my L is going to end up being velocity divided by 2 times frequency. I'm going to get this 2 down here. So 343 divided by 2 times my fundamental frequency of 370. This ends up being a length of 0.46 meters. So in order to create a fundamental harmonic of 370 hertz, I'm going to need that's a pipe that's open at both ends of 0.464 meters. Now, if it happens to be closed at one end, now that length of that tube, that's going to be 4 times as much now for my fundamental wavelength. So now my fundamental wavelength is not going to be, it's going to now be 1.86 meters as a result. That means that my fundamental harmonic, I'm going to rearrange my wave speed equation here. And so I'm going to take the speed of sound, 343 meters per second, divided by my new wavelength of 1.86 meters. And I'm going to find out that in this case, my fundamental frequency is 184 hertz. Okay? My next harmonic that I could get is not going to be double this, it's going to be triple this. So my next overtone here is going to end up being right here. The next harmonic is going to be the third times that. So I'm going to take that, that's going to be 552 hertz. I'm going to take that 184, multiply it times 3. My next harmonic that's possible is going to be 552 hertz. Okay? So, for next time, you've got an assignment. It's not very long, but you should have a weekend coming up of 4 days without your distance learning. So, enjoy.